Sharma. I'm a cybersecurity data scientist at Coursera, and I'm really passionate about natural language processing and reinforcement learning.
Hello everyone, my name is Rakesh Kumar and I'm working as a data scientist at AI in Bangalore.
Hello, I'm Jacob from South Korea, and we are actually just starting data science education universities in UBC. And in South Korea, I have some experience working for Hyperconnect Kazan as a data engineer. Thank you.
Hi, my name is Aichi. I'm a data scientist at Lambda Plus. I'm interested in machine learning and object recognition.
It's fine. I don't like the echo as well. Hi, I'm Sumit. I'm a recent graduate from UBC. I like to scale large models on the weekend and large amounts of data on the weekend. And I'm excited to be here to look at natural language processing and philosophy. And I hope to speak soon. So I'm here to see how this goes on. Nice to meet you all.
Hi everyone, so it is my turn. So before I start my presentation, I just want to say I had a COVID 2 months ago. I'm completely recovered now, but my throat is not well yet, so I may have to occasionally cough during my presentation. So if I cough too much, my apologies in that regard in advance. So I would like to start this presentation by saying thank you to Learn Data Science Group for giving me this opportunity to speak at Kaggle Competition Talk. Also, many thanks to Red Emery for organizing this event. Many thanks to Deb Messer and Sal Rahman at Tech Meetup Vancouver for promoting this event. And most importantly, thank you, my dear audience, for coming out today or watching online to listen to me. I'm very happy to see you all in person and online. I have to say that about 3 years ago, I was one of the audience members listening to Kaggle presentation without knowing anything about data science, being so fascinated by it. That point of time was the beginning of my career change. And now I am presenting Kaggle competition myself. So today is my very first day as well. Also, it is first Kaggle presentation after Kaggle talk was on hold for almost 2 years. Mainly due to COVID. So we have many reasons to celebrate it. So the Kaggle competition that I'm presenting today is natural language processing with natural disaster. So first and foremost, let me introduce myself. I'm currently working as a data scientist at Vancouver-based software company. Before my career change to data scientist, I was working in accounting and finance for over 10 years. 2.7 years are the number of years it took me to transition my profession from accountant to data scientist. And I hope to grow as data scientist much longer than this number of years, days, hours, minutes, and seconds. I graduated from master's degree program in management analytics at SME School of Business in Queen's University last year. I have been studying in data science and machine learning program at McGill University since last year, and recently I completed data science bootcamp at Lighthouse Lab. I have worked on various projects such as Capstone with SAS Institute, designing machine learning game scenario, recommender system using R, predictive models on financial data and flight delays, NLP projects on Amazon Review and with transformers, and generative AI art that involves computer vision, including DALL-E 2, and AI art is my ongoing project. I also love collaborating with others on other projects, so if you are interested in working with me on other Kaggle competitions or hackathon, or possibly publishing paper, please feel free to contact me. So this Kaggle competition challenges to predict tweets related to real disaster. Why did I pick this competition? This competition is ongoing knowledge-based Kaggle. Knowledge-based competition is a great way to learn machine learning concept while getting familiar with Kaggle platform. You can build out further from the basic concept. As it is non-competitive Kaggle, there is no cash prize and on a rolling timeline. But everything else was the same as other competitive Kaggle competition, where you submit your results to the leaderboard and your results are being evaluated and ranked among other participants. This Kaggle was not entirely for a newcomer, however, as I needed to have experience working with machine learning and optimizing its performance. This competition was perfect if I wanted to brush up on NLP, as it was designed to introduce data scientists to natural language processing text classification with various machine learning models. I was also interested in working with Twitter data and applying natural language processing to it. The primary objective of this Kaggle is to predict disaster-related tweets with high accuracy by optimizing text classification machine learning algorithms. Also, I did a sentiment analysis on disaster tweets, which was not part of this Kaggle competition. And the main objective for that was actually without any particular reason. If I may add pedagogical reason for this, it was to determine data analytic methodology to identify the level of crisis and to help improve emergency management system. So why Twitter? Each social network app such as Facebook, Instagram, Reddit, and TikTok has marginally different platform and content generation technique. Twitter has become an important communication channel, especially in times of emergency, and there has been a growing interest of monitoring Twitter along with other social network apps. The primary reason for that is that people on smartphone announce and react to emergency in real time, especially when they are directly affected by disaster, like the alien invasion, for example, here. Tweets also provide useful sentiment-based data. The study showed longer tweets were more likely to include useful sentiment-based or emotional content. More popular tweets were likely to include useful information about the disaster, and negative sentiments were expressed more often in areas with young families. Twitter is also location-based social network, and it can include geospatial component. This gives a great advantage compared to other social media platforms. These factors enable us to monitor and analyze the social media chatter during a disaster, and it helps decision makers learn how to plan for and mitigate the impacts of severe events in our communities, which leads to developing a new method for measuring social cohesion, which is an important factor in our community resilience. This is the process I took to complete this Kaggle competition, and I will be presenting in the order of this process. I started with EDA, exploratory data analysis, to study the patterns and distribution in text data, and to gather other insights through various visualizations. Then I performed text pre-processing and feature extraction to prepare data for machine learning algorithms. The various machine learning models were trained and tested using data prepared, and based on the results of model performance evaluation, best machine learning models were selected, and their results were submitted to Kaggle leaderboard. I further performed the sentiment analysis and calculated the sentiment scores. Kaggle data consisted of trained and text data of about 10,000 tweets altogether, where trained data had 7,613 samples and test data had 3,263 samples. These tweets were largely from August 2015 timeframe. Twitter data is unstructured if you obtain them through Twitter API directly. But because this was Kaggle competition, the Twitter data were provided in structured data format in CSV. Both data sets had four main variables: ID, keywords, location, and text. The text and ID variables had no missing values, whereas keyword and location had almost 30% to 40% missing values. And their unique values included text data that did not have much meaning to disaster. For example, location or keyword included numerical values combined with character or punctuation or random words like "where are you?", "disaster", "World Wide Web", "Earth", and so on. So for EDA and sentiment analysis process, I extracted valid text values that had actual context for disaster and had high relevancy for location and keyword variables and filtered out the rest. The text variable was body of the tweet, and this variable was used for text pre-processing and machine learning model training. The trained data had target class of 0 and 1 for text classification machine learning training, where 1 for disaster tweets and 0 for non-disaster tweets. And these classes were manually labeled. Before moving on to any formal process, I did a preliminary data preparation on training data set by first removing duplicate tweets, where there were about 110 duplicate tweets. Then I observed that target class was imbalanced in the training data set, where non-disaster target class had 40% more tweets than disaster target class. So I balanced target class by randomly resampling non-disaster related tweets to approximately match to the amount of disaster tweets. Through this process, about 800 non-disaster tweets were randomly removed from the training data set, and you can see the end result in a bar chart for the balanced data set. So EDA is a process by which data scientists and data analysts become acquainted with their data to drive intuition and begin to formulate testable hypotheses. This process typically makes use of descriptive statistics and visualization. I did EDA mainly for statistical and term frequency analysis to capture pattern and distribution in text data, or data representation to help understand the meaning of text data by visualizing any commonly used keywords, topics, or features. The EDA was also important during a sentiment analysis. Location variable in Twitter was not probably ideal for doing this EDA due to its significantly missing values and highly unstructured data content, where country and city names were mixed along with inconsistency with country and city names. For example, US and USA and United States were practically the same country, but Python did not recognize as such unless I apply regular expression on these various terms. And there was another complication, mainly due to lots of noise in this variable. So although I managed to come up with this visualization, it comes with high statistical variance and relatively low accuracy due to that reason. And at least you can get the idea as to what location data looks like. For EDA on a Twitter location, I filtered out non-disaster tweets and did the visualization only on a disaster tweet. Also, the more dense the color in the visualization, the more tweets there were. Tweets were highly concentrated in USA and then were dispersed worldwide, such as India, Nigeria, UK, Canada, Australia, Indonesia, Ireland, Scotland, Kenya, and so on. When breaking down those dense regions to cities for US, India, UK, and Canada, this was the kind of distribution that I was able to get, where city with the most disaster tweets in the US was New York. For UK, it was London. For India, it was Mumbai. And for Canada, it was Toronto. For capturing keywords from text variable in both disaster and non-disaster tweets, I did EDA with word cloud and horizontal bar chart with most frequent unique words. In disaster tweets, you can see words like fire, suicide, news as the most frequent unique words, whereas non-disaster tweets show like, get, want, and time as the most frequent words, which may be representative of overall sentiment between disaster and non-disaster tweets. Stop words analysis for EDA in NLP is very common. I may be going back to Data Science 101 by explaining this term, but stop words are basically a set of commonly used words in any language, not just English. In English, it would be words like and, as, eat, that, which do not add any values to the text feature. Here, I am observing the most frequent stop words in tweets. And out of all stop words, The 5 most frequent stop words were the, a, to, in, of. Another common EDA on NLP is distribution plots on various counts and frequency on characters and words on raw text data. I generated 18 distribution plots, where first 9 plots were for distribution between disaster tweets and non-disaster tweets, and the other 9 plots were for distribution between training and test data sets. For this presentation, I'm showcasing 9 plots for distribution between disaster and non-disaster tweets, where disaster tweets are in red color and non-disaster tweets are in green color. First 2 distribution plots that you are seeing here are character counts and stop words count distribution plots. I will not go through my notes here, as they are pretty straightforward observation. Only thing I want to note here is that the Twitter changed its character limit from 140 characters to 280 characters on November 8, 2017. As the Twitter data in Kaggle was dated August 2015, which was before that change was made, the maximum character that you see in this character count plot does not exceed 140 maximum. Also, another thing to note is that the intensity of distribution in disaster tweet is higher than that for non-disaster tweets. These are the distribution plots on word count, mean word count, unique word count. Each plot shows different patterns of distribution from one another. You can still see the higher intensity for disaster tweets, except for mean word length plots. Here are another distribution plots on hashtag counts and mention counts. The interesting thing to note is that for the hashtag count plot, when no hashtags were used in tweets, the intensity of disaster tweet is much lower than that of non-disaster tweets, which makes sense. However, for the mention count plot, it was exactly opposite of that pattern. Here are the last distribution plots on punctuation counts and URL counts in tweets. You can see that the disaster tweets include more punctuation than URL and non-disaster tweets. So I took 3 steps for text classification: text pre-processing, feature extraction, and machine learning model training. As for text pre-processing process, applied step-by-step pre-processing technique for supervised learning. For deep learning, I use either the same step-by-step text pre-processing used for supervised machine learning, or text pre-processing using a TensorFlow Keras pre-processing hub. For data representation and feature extraction, I conducted n-gram analysis and topic modeling to understand the context, topics, and relationship among terms and topics in training data set. For machine learning training, text data were converted to numerical vector data suitable to be processed by supervised machine learning models. For deep learning transformer models, I took the approach necessary for building neural network or for pre-trained model. So the training data set for supervised machine learning, deep learning, and transformer models were completely different processes. This slide is just to provide demo of what is happening in my text pre-processing process for supervised machine learning models. You can see the changes that would happen in the original tweet as each pre-processing task is executed. And my text pre-processing algorithm was ordered to perform each task precisely in this order. Text pre-processing was done in 2 procedures. The first procedure was applying the full list of pre-processing techniques, as you can see here, and afterwards, the pre-processed text data from the first procedure was first processed to remove characters without any meaning, as you will see it shortly. I think my demo is done here right now. There are a number of ways to do the feature extraction for data representation. The n-grams analysis can provide a semantic insight on Twitter. In this 5-grams analysis, which shows the most frequent phrases in 2-word sequence, you can get the general idea about the kind of disaster being communicated in Twitter, such as suicide bomber, burning building, and locations of these disasters. Diagrams on non-disaster tweets were sort of random. The last three phrases could indicate a potential disaster, although these tweets are non-disaster tweets. Continuing with the n-gram analysis, this slide shows trigram analysis with the most frequent phrases and three-word sequence for disaster and non-disaster tweets. Trigrams can add more context to diagrams. You can better sense what the tweets were about. The disaster tweets include content such as wildfire, thunderstorm, outbreak, suicide bomb, or oil spill, whereas non-disaster tweets include quite random topics related to stock market, breaking news, or possibly bomb detonation. I also did LDA topic modeling as part of data representation and feature extraction process. Topic modeling in general is a type of statistical language models used for uncovering hidden structures in a collection of text, which involves a task of dimensionality reduction and unsupervised learning that builds clusters of words rather than clusters of text. Latent Dirichlet allocation, or LDA, is a generative probabilistic model that assumes each topic is a mixture over underlying set of words, and each document is a mixture over a set of topic probabilities. We can see the basic architecture of ADA topic modeling here. In the generative process of ADA, with given n number of documentations, n number of words, and prior k numbers of topic, the topic model trains pre-processed text to two outputs. Psi, which is distribution of words for each topic k, and phi, which is distribution of topics for each document I. LDA has two parameters, alpha that represents document topic density, and beta that represents topic word density. I will be showing 3-minute demo of LDA topic modeling results of the Kaggle Twitter training data in an interactive visualization shortly. I separated training data to disaster tweets and non-disaster tweets, and use the PyLDA visualization package to visualize and create the LDA topic modeling visualization for these two sets of tweets separately. ADA visualization on this slide represents disaster tweets. You can see 7 topics in clusters on the left, and list of words for these topics on the right. This visualization is designed to help interactively with better understanding and interpreting individual topics, and better understanding the relationship between the topics. For understanding individual topics, you can manually select each topic to view its top most frequent and relevant terms. And I'm going over each topic cluster here, and the list of relevant words changes as I move from one topic cluster to another. I can also select a word in the list of words, and you can see the topic clusters related to that word, which appears in a varying density. A word wildfire, for example, appears in topic 7 and 2, higher density in topic 7. The word suicide appears in topic 1 and 5. A word bomb appears in topic 1 and 5 with the highest density in topic 5. Word earthquake appears in topic 2, 3, 4, and 7, where topic 7 cluster has the highest density of this word. I can also check the list of words for each topic at varying degree of values in the lambda parameter, as you can see in this demo. This can help when you are trying to assign a human interpretable name or meaning to each topic. You can also determine what each topic is related to by doing this exercise. For understanding the relationship between topics, exploring the intertopic distance plot can help you learn about how topics relate to each other, including potential high-level structure between groups of topics. And this is another LDA topic modeling visualization for a non-disaster tweet. You can see 5 topic clusters in this group with this kind of list of words that each cluster has. And I'm just going one cluster to another and observing this words whole life cluster here right now. I think my demo is done here. For the process of machine learning model training, I took different steps for supervised machine learning models, deep learning models, and transformers. For the supervised machine learning models, I trained all the models with the pre-processed training data set and applied two types of word embedding technique using scikit-learn separately, bag of words and TF-IDF. Then I selected two high-performing models after comparing their performance results and hyperparameter tuned them. After obtaining optimal parameters, I predicted on test data set with these models and submitted the result to Kaggle leaderboard. For deep learning models, I trained two models, MLP and LSTM-based RNN. As for NLP classifier, I built neural nets through scikit-learn neural network function and library and hyperparameter tuned my research to optimize model training. As for LSTM-based RNN model, I used TensorFlow Keras library to build neural nets and constructed layers for RNN. For pre-trained transformers, I tested three transformer models, BERT, Distilbert, and Roberta. The general steps that I took for these models were defining each pre-trained transformer and tokenizing datasets by adding tokens encoded under TensorFlow transformer packages and train the model after setting the training argument. For BERT, however, I set the base model with neural networks by specifying the neural network layers instead of defining the model for transformers. The overall performance of machine learning models looks something like this, where evaluation of the machine learning performance computed by the Kaggle platform was based on F1 score. Out of all the supervised machine learning, deep learning, and transformer models that I tried, the winner was Roberta transformer model, which scored 0.83726 in F1 score. This summary chart shows the overall performance results of all the supervised learning models that I tried based on F1 score that I computed. Blue bar is for the results after bag of word embedding technique was applied, and green bar is the result from TF-IDF word embedding technique to each machine learning algorithm. It is generally understood that the machine learning with TF-IDF performs better, but in my case, machine learning models with bag of word perform much better than those with TF-IDF. Bag of word applied to Gaussian naive Bayes did not perform at all for some reason, and I do not know what happened there. Based on this result, I selected logistic regression and SBC classifier for hyperparameter tuning. For the next two slides, it can be data science 101 again for some people here, but please bear with me. And as I am briefly going over two feature extraction techniques that I use. The text data is generally messy and unstructured, but machine learning algorithms prefer structures, well-defined, fixed-length, numerical data inputs. Bag of word is one of representation technique of text that converts text data to data input more suitable for machine learning models, while extracting text features that describe the occurrence of words within the document. This approach is relatively simple and flexible compared to other feature extraction technique where it converts variable length text into fixed length vectors or its equivalent vector of numbers. Bag of word involves vocabulary of known words and measure of the presence of known words, where scoring of each document looks like a binary vector, which is illustrated in the table on the slide. For vectorizing text data with bag of word technique, I use counter vectorizer under scikit-learn Python library as shown here. TF-IDF is another representation technique of text, which is numerical statistics intended to reflect how important a word is to a document in a collection or corpus. This is mathematical illustration of how TF-IDF works, where it has two sections, term frequency and inverted document frequency. The key concept in this technique lies in how the importance of a word is defined. Words are considered important when they are frequent in a document, but not across documents. So the more unique words appear to be across the document, the higher their TF-IDF score is, which is computed by this map. For vectorizing text data with TF-IDF technique, I use TF-IDF vectorizer under scikit-learn Python library is shown here. Both backup words and TF-IDF have dimension issues. The vocabulary size from backup word and TF-IDF can get very, very large with more sparse matrix and over more than 100,000 features. The backup words would be worse in this case, but I apply dimensionality reduction and data normalization on TF-IDF vectorized data only. To reduce the number of dimensions, I apply principal component analysis or PCA on top of TF-IDF matrix. This table shows explained variance for each PCA component in the order of its importance, where explained variance is a statistical measure of how much variation in the dataset can be attributed to each of the principal components or eigenvectors generated by the PCA method. In general, explained variance for PCA components in percentage was very low, where the highest explained variance was 0.69%. So for applying PCA, I limited dimensionality reduction up to 200 PCA components from over 1,200 dimensions. These PCA components had explained variance over 0.15% at least. For data normalization, I used min-max scaler, which normalized vectorized text data based on its maximum and minimum vector values and scale the data in the range from 0 to 1. I found this scaler more suitable than standard scaler, where standard scaler would standardize the data based on the normal distribution with mean and standard deviation that generates negative standardized values. From this process diagram, for clarity, I wanted to show what process I was taking for training models with TF-IDF. This process was purely for testing whether TF-IDF with PCA and scalar performed better or not. Based on the pre-processed text training data, which was vectorized with TF-IDF, I created two separate data samples. One data sample with PCA and min-max scalar, and the other data sample without PCA and min-max scalar. I trained two selected machine learning models, logistic regression and SVC, with each of these two data samples. And I hyperparameter tuned them separately as well. Afterwards, a Kaggle submission file was created separately for each of these models and samples. I could have taken the same process for backup words as well, but I did not choose to do so because I was thinking that backup word would have similar results as TF-IDF, and I was also thinking that the machine learning models with TF-IDF would perform better. This was what F1 scores computed by Kaggle platform on each submission look like. Blue bars indicate models without PCA and scalar, and orange bars were models with PCA and scalar. The logistic regression performed slightly better than SVC, but what was interesting here was the fact that both machine learning models with PCA and scalar drastically did not perform well compared to the models without PCA and scalar. This result makes sense in a way because by reducing dimensionality and normalizing data, the features and context of text data, which could have been important factors for text classification prediction, might have been significantly eliminated. So the performance might have been not optimized well. My apology for this very busy slide here. I hope you can see and read. Anyway, here is a detail of hyperparameter tuning for logistic regression with and without PCA and scalar. I don't think I'm going through all the details in this slide, but there are two things that I want to point out here. One is processing time. The logistic regression with PCA and scalar ran much faster than the model without PCA and scalar because dimension of vectorized data was reduced and data was normalized. The other is that for grid search, I used the same parameter grid for both with PCA and scalar and without PCA and scalar. And as the data structures are different between them, the best parameters determine research were different. And logistic regression without PCA and scalar performed better by 45%. Here I have another busy slide. Here is the detail of hyperparameter tuning for SPC with and without PCA and scalar, where SPC's running time was much longer than that of logistic regression. Two things that I want to point out. One is, again, the processing time. But in case of SPC, the processing time is not comparable between SPC with PCA and scalar and without PCA and scalar because I use different research algorithms. SPC with PCA and scalar took about 2 hours, 21 minutes to run, but SPC without PCA and scalar could never finish, as its running time exceeded more than 24 hours with the same research algorithm. So for this instance, I used Halving research algorithm instead to significantly reduce the running time for hyperparameter tuning, which then took only 15 minutes to run. The other point is that the parameters set between research and Halving search were the same. The best parameters determined by research and Halving research were again different between SPC with PCA and scalar and SPC without PCA and scalar, as you can see here. And SPC without PCA and scalar again performed better by 41%. After supervised machine learning, I moved on to deep learning, and I trained two different deep learning models, MLP classifiers and LSTM-based RNN model. And these models needed to be built before they were trained. We normally think Keras, PyTorch, or TensorFlow for deep learning, but scikit-learn library is also capable of basic deep learning modeling. An MLP classifier was developed for binary classification under this machine learning library. I would like to direct your attention to the figure 1 diagram for a second. The multi-layer perception, or MLP, is a feed-forward artificial neural network model that maps input data sets to a set of appropriate outputs. MLP consists of multiple layers, and each layer is fully connected to the following layer. The nodes of the layers are neurons with nonlinear activation function, except for the nodes of the input layer. And between the input and output layer, there may be one or more nonlinear hidden layers. Unlike other deep learning models, this model has supervised learning algorithms that learns from this map when trained on data set. Because it works in supervised learning algorithm, I could use TF-IDF vectorized data and train the model with or without PCA, and I could also hyperparameter tune the model. The result of Kaggle 1 scores looks something like this, where MLP without PCA and without hyperparameter tuning had highest F1 score. Another deep learning model that I trained was bidirectional LSTM-based RNN, which was built under TensorFlow and Keras library. I will not go into details about RNN and LSTM, but RNN has the issue of vanishing and exploding gradients with difficulty of training, and LSTM network, which is a modified version of RNN, resolves this very issue using backpropagation and its refined architecture. The research paper that introduces architecture of LSTM-based RNA came about in 2014, if I am not wrong. So this architecture was with us for a while. The basic architecture of my model that I trained looks something like this. I could not fit everything into this diagram because my input layer is missing here. The model started with bidirectional RNN with 256 nodes, which is missing in this diagram. And then, as you can see in this diagram, it has 3 stacked LSTM, each with 128, 64, and 32 states, with dropout layers in between, and 2 dense layers, each with dropout layer. And the last layer was output layer. I added kernel regularizer to apply penalties in each LSTM layer, and for each dense layer, I used RALU as my activation function, and the activation function for my output layer was sigmoid function. And for those in the audience who may be wondering what dropout layer is, The dropout layer randomly sets input units to 0 with frequency updated each step during training time. It helps prevent outfitting by doing so. Introducing penalties through regularizer is also another way of helping preventing overfitting issues and improving the accuracy. And just for fun, I trained this model with both fully preprocessed text data and preprocessed text data to see the difference. When looking at the Kaggle 1 scores, there is not much difference between preprocessed and unpreprocessed text data. The model performs slightly better with preprocessed text data by 0.3%. But when we look at the model accuracy and loss while the model was being trained, the accuracy for preprocessed text data improved much better than the model trained with the unpreprocessed text data, although the reduction in loss was better with unpreprocessed text data. This seems to tell that this deep learning model works better with fully preprocessed text data, but it could be misleading to make that assumption, as some features such as stop words, punctuation, or any numbers could have impact on model prediction, which needs further experiments. Now, we have waited for this very moment, and we went through so much to get here just to see transformers, and thank you so much for waiting. For me, using transformer models was so huge, and it was the most exciting part of working on this Kaggle competition, as it was a game changer for text classification. Just as a side, I realized names of transformer models were adopted from Ernie and Bert in Sesame Street, so I put their images for fun. Apparently, each Muppet has its own Twitter account, and the difference in their Twitter setups went so wild in social network 2 years ago. I also started to wonder why so many AI systems were named after Muppets. The answer to this question would probably have to be another presentation that has to do a lot with how AI system was developed. Anyway, there were a number of major NLP projects for BERT, such as Flow, Transformer, Attention is All You Need, or Elmo. But after the birth of BERT by Google in May 2018, there have been hundreds of other transformer models, which are variation of BERT. And these transformers have been created by various developers and companies. The timeline chart that you are seeing on this slide only shows number of transformers in 2019, which are not all. Out of these transformers, I used BERT, DistillBERT, and Roberta for text classification. So I started with BERT for experimenting with transformer models with text classification. The transformers are pre-trained models, and these models do not require excessive text pre-processing process like supervised machine learning. For BERT, I used TensorFlow's text pre-processing APIs built in BERT preprocess off in TensorFlow for inputs to BERT model. BERT, or bidirectional encoder representations from transformer, is a transformer-based machine learning technique for NLP pre-training, which was developed by Jacob Devlin and his colleagues in Google in 2018. This transformer was later leveraged in Google search engine. And BERT is a bidirectional model as it learns the context of word based on all of its surroundings, which are left and right of the word, and has a attention mechanism that learns contextual relations between words or subwords in the text. This diagram shows architecture of BERT transformer. In general, transformer use encoder that reads the text input and decoder that produces prediction for text classification. But BERT only uses encoder to learn latent representation of input text, as shown in this diagram. Input is a sequence of tokens, which are first embedded into vectors and then processed in the neural network. The output is a sequence of vectors of size h, in which each vector corresponds to an input token with the same index. The size of BERT can be based on two different architectures, either BERT base, which has 110 million parameters, or BERT large with 345 million parameters, and its size can be determined based on whether it is small-scale task or large-scale task. The second transformer model that I experimented was DistillBERT, which is small, fast, cheap, and light transformer model trained by distilling BERT base. was developed by Hugging Face as an open source model. The Stillbird model has 40% less parameters and bird phase and pace. It runs 60% faster while preserving over 90% of bird's performance as measured on the Glue benchmark. You can implement the Stillbird with TensorFlow and Keras by following 3 steps. So the first step, by using train the Stillbird to generate sentence embedding for a training data set, and using basic dense and dropout layers for further classification and training, and finally by evaluating the model. In my case, I used TensorFlow for tokenizing train and test data sets, and used pre-trained the Stillbird transformer for fine-tuning without specifying any layers for the model, which was a very simple process, and the Kaggle result was satisfactory, which gave me over 0.83 F1 score. Roberta, for robustly optimized bird pre-training approach, was developed and presented by researchers at Facebook AI at Washington University based on Google's bird transformer model. And it was developed to optimize the training of bird architecture in order to take lesser time during the pre-training. The architecture of Roberta is very similar to BERT, but there were 3 main changes made to BERT model for improvement. And I will go over these changes in detail in the next slide shortly. There are 4 main data sets that are used for training Roberta model: book corpus, CC news, open web text, or stories. The model that I used was Roberta OS, which was pre-trained on a large corpus of English data in a self-supervised fashion, and also pre-trained on the raw text only without any human labeling. And Roberta model performed the best among all the transform models that I experimented with. So let's find out the detail of 3 main changes made to BERT architecture that contributed to better pre-training and performance in Roberta model. You are looking at the architecture of BERT model on this slide right now. The one change was removing the next sentence prediction or NSP objective in BERT architecture. By removing NSP, the loss slightly improved the downstream task performance. The second change was training with much bigger batch size and longer sequences. The batch size was increased from 256 to 2048, and the sequence was increased from 30,000 vocabulary to 50,000 vocabulary by increasing the size of parameters from 108 million to 123 million. You may think something along the lines of, like, I definitely cannot train that on my GPU, or I don't have those machines with 64 gigabyte of GPU memory. Well, it turns out that you can use gradient accumulation, which allows training with large batch size, even with low memory resources. This technique can easily be integrated with deep learning frameworks under TensorFlow and Keras as well. There were 2 advantages with this change. The large batches improved perplexity on masked language modeling objective, as well as end-task accuracy. The large batches were also easier to parallelize by a distributed parallel training. The third change was dynamically changing the masking pattern. This change was made to avoid using single static mask resulted from BERT during data pre-processing. And you can see the Roberta scored 88.93% in Glue benchmark, which is higher than what BERT model scored. This table summarizes the comparison of BERT, the Stillbird, and Roberta transformers very well. With respect to Kaggle performance, Roberta performed the best in my text classification task, but when looking at the comparison in each category, depending on tasks and projects, we can make trade-offs regarding actual model deployment. For example, Roberta's performance is 2 to 20% better than BERT, but its training time takes 4 or 5 times more than BERT, and it uses much more data than BERT and the Stillbird with 160 gigabytes of data. The Stillbird may not perform better than Roberta, or sometimes worse than BERT, with 3% degradation from BERT in its performance, but it uses much smaller base, and its training time is much faster, which is 4 times less than BERT. So this is my position at Kaggle Leaderboard with my smiley happy face, or maybe you cannot see it. I was at a 53rd position out of 718 teams. So with Roberta Transformer, I was able to position myself within top 7% of this Kaggle competition. Yay. But I never understood why, how many people were able to achieve 100% F1 scores, and it still remains a mystery to me. Because this Kaggle competition is ongoing knowledge-based competition, there has not been any solution posted for 100% F1 score, and I don't think these people want to share their solutions. In addition to text classification tasks for this Kaggle competition, I performed sentiment analysis on training data using Gator sentiment analysis tool. Because this competition was not designed for sentiment analysis, Kaggle data was not prepared for doing this analysis, so I used Gator pre-training model to do this task. Gator, or the Variance-Aware Dictionary and Sentiment Reasoner, is a lexicon and rule-based sentiment analysis tool that is specifically attuned to sentiment expressed in social media. It is fully lexicon-based concept, which uses a combination of sentiment lexicon and a list of lexical features in words, and gives us positive, negative, and neutral scores of the sentence. So the sentiment scores were calculated by Gator sentiment analysis tool. For negative sentiment, the sentiment scores ranged from -1 to -0.05. For neutral sentiment, the score ranged between -0.05 and +0.05. And for positive sentiment, the scores were greater than 0.05, all the way up to 1.0. When looking at disaster tweets alone, there were tweets classified as positive, neutral, and negative sentiments, but the proportion of negative sentiments was much higher when compared to non-disaster tweets. And we can observe that in both visualization on the slide, especially in sentiment score distribution only for disaster tweets on the right. The counts of the negative sentiments are in much higher intensity than the counts for positive sentiments. These sentiment scores are further used to determine the level of severity of disaster. For example, -0.98 for more severe crisis and +0.90 for least severe crisis. Based on the result of sentiment analysis, disaster tweets were classified into 3 classes and subclasses of disaster. In the training data set, most disaster tweets were man-made disaster, which represented 59% of training data, where 29% out of 59% of training data where 29% out of 59% was related to intentional disasters such as suicide bomb, shooting, or terrorist attack. And 30% was related to accidental disasters such as car crash or oil spill. 30% of disaster tweets were related to natural disaster, including hurricane, wildfire, tsunami, earthquake, and epidemic. These natural disaster tweets were further subdivided to meteorological, climatological, hydrological, geophysical, and virological disaster. And 11% was related to other category not relevant to disaster. I found that the text classification and sentiment analysis can have huge impact on emergency response management for disaster control. Their use case can potentially be on analytic activities as a part of emergency management cycle that has 4 key components, which are preparation, response, recovery, and mitigation. The analytic activities can trigger the action required for appropriate response for recovery and preparation, and also provide valuable information for recovery and mitigation phase of the emergency management cycle. As a rough use case design as to how we can incorporate this concept into system, the analytic activities can start with text mining from Twitter API, and then model is deployed for text classification for disaster tweet prediction and for sentiment analysis for disaster ratings to determine the crisis level with sentiment scores. The transformer models will also enable us to retrieve and collect the semantic context of these tweets when we send specific queries to this system. So this is the end of my presentation. Thank you very much for listening, and I will now open the floor for questions.
I can just run around and give everyone the mic. But first, please, round of applause. And I'll just ask the first one. Why do you think that distilled word worked better than like just BERT in your scenario?
I think I will be going back to the comparison table just to answer that question. So first of all, the silver is much light sugar. It's actually, it uses much smaller parameters than BERT. And I think that if you can see, hold on a second. So I'm going back to the silver transformer model. So first of all, this model is like very small and fast, cheap, and light transformer model trained by distilling BERT base. So it's actually coming from the BERT base, but it uses the BERT base interface, and then it's transformed to become a distilled BERT. And because it uses less parameters, I think that it does a less computation in the architecture itself, and then it uses, I think, much smaller data to pre-train, but it performs much better. And I don't know the detail as to why exactly it performs much better than BERT, but I think one of those characteristics definitely contribute to the better performance. And I'm not sure if anyone in the audience can answer better than myself, actually. Is anyone willing to add any comments to this question? No? Okay. All right.
Any other questions? Okay, just a hypothesis. Because we're all just for the live stream. Yes.
Okay, just because, so there are three models, right? The one which is, can you hear me? Yeah, so there's BERT, there's Roberta, and there's distilled BERT. Roberta has this removes the next sentence prediction objective, which I think is relevant when you're trying to predict for trees. So does that same thing happen with distilled BERT? That's why it is able to reduce the parameters that it needs, because it removes the objectives that which are demanded, and so it is able to become more accurate as well and faster. Am I on the right track? Maybe Matt can help.
That seems plausible, right? If you're just trying to predict the mask using distilled BERT, yeah, actually, I think that's a pretty good idea.
Yeah, sorry. So I think it's very happy. So I think that's how we come for gas as well. Another thing is
I think you are asking about the silver right now, right?
Yeah.
Vision to BERT. Yeah. So because the silver has to be much simplified from BERT, so a lot of function and architecture has to be stripped down to make the silver happen. So I think, I don't know exactly what happened, but I think one of the guys is definitely some of the changes, like some of, for example, like how the process might have been eliminated to become a simpler version of BERT. So that could be another case. But I know, yeah, it's a much simpler version of model, but it performs much better than BERT.
Anyone else have questions?
So each topology is only added for EA part, or you can write topology in I2 mode as well.
So the question was just if the LDA, the unsupervised topic modeling part, was that used in, say, part of the pipeline feature extraction, or was that something separate?
Yes, I used along with sorry. So hold on a second. Okay. So for coming up with LDA visualization, first of all, I use the fully pre-processed text in the training data set. And then there's some of the steps that I have to follow to make that happen. So it's not exactly the same as other process that I was taking. LDA has to be taken in a separate procedure to create that visualization. But pre-processing was one of the steps. And then you will train using the LDA model that I sort of explained. So then you go through dimensional reduction on the data, and then you go through the, I should say, hold on a second. Supervised learning. So I use a supervised learning model, which is LDA, to train the data to come up with clusters for the topic, which pulls the word for each list of words, the term of words related to each cluster. And then the way it is done is based on this architecture, but it calculates the distance between each word, and whatever the shortest length that calculated for the cluster, then that cluster becomes one topic. And then that's how the ADA topic modeling was created. So it was kind of a different process from our other EDA in the feature section that I was doing.
Next question.
Well, thank you so much for the presentation. And I just had one question about the visualization part in the start. So you mentioned that we count the number of stopwords and some other parameters, and we compare the targets for disaster tweets versus the normal ones. So I was just interested to know, is there any way we can incorporate this in the machine learning model or in other types of models that we can kind of use hyperparameters so that we can we have that observation and now use it in our models to make it better?
Thank you very much. Yeah, that's a good question. Usually, EDA is kind of separate from machine learning training because data, kind of data that we use for EDA and machine learning training is completely separate and different. Because for machine learning to recognize the data and be able to train, you have to vectorize the data and convert the data to the data that's suitable for machine learning to recognize. So whereas EDA was kind of same, but completely different. So there are feature extraction that sometimes we adopt as a part of the parameters. And when we optimize the machine learning, it's based on the kind of parameters that you are working with. So one of the parameters in machine learning training, for hyperparameter training, for example, there's an n-gram. And I think I show you n-gram analysis, i-gram, tri-gram. You can use that same feature in a machine learning optimization process, a part of the feature extraction. As a part of the parameters, you can specify, and then you can optimize machine learning that way. But the EDA and machine learning training is sort of separate process.
Yeah, I'm just curious. You did also data regressions, right? You did it on like simple models and then you went forward. What I was wondering is that, like you suggested, that New York was one of the high densities of streets, right? From New York, Mumbai, and Toronto. And did you check just in a specific way from New York what kind of streets were more common, like buildings? And sorry, can you hear me? Oh no. Oh, very light. Okay. Sorry. I'll be more loud. What I was just suggesting is like when you were trying out your simple models, And since the countries were mostly dense around New York, Mumbai, and Toronto, and also I was curious why the hashtags and the ad signs weren't very useful in the analysis, because I was thinking like, when you have hurricanes, you have like hashtag, I don't know, Bella hurricane happening in some state of United States of America, but which is interesting that that wasn't the case. But did you try out specific models like a linear regression and see the accuracy? How did it change between like New York, London, or Toronto?
Well, yeah, I didn't get to do that experiment, but that would be very interesting to do. And what I can learn further.
And if I say this, it's actually, I'm not sure if I'm responding to your question as well, but I did hashtag counts and mention counts, not specifically for machine learning purposes, but it's a part of the sentiment analysis. Because sometimes hashtag counts and mention counts contribute to what the sentiments of people were. So that's part of the analysis. But for machine learning, it's not very useful unless you're using transformer, for example, because transformers sometimes extract this feature as well for machine learning performance. For supervised learning, you can't really use this value because you have to fully pre-process the text data. So for machine learning purposes, this is to find out, okay, for text pre-processing, these are the values that I have to eliminate. So it's one of my preliminary steps for cleaning out the data or prepare for the machine learning process, not so much for transformer or deep learning, however. And then this EDA is actually mainly for sentiment analysis. So it applies to that part of the analysis, but not so much for machine learning. But I think the one you mentioned earlier is that I think that's an experiment that I'll definitely try. I want to try out to see what I can observe.
Yeah, so for the sentiment analysis, I'm really curious, did you use any text mining or other data mining techniques? And how did you make those data visualizations?
Could you provide example, like say, kind of text mining that you have in mind?
Yeah, it was.
What is your next one?
Yeah, I'm not really familiar with those text mining in details, but I do know like there's one slice you mentioned for the sentiment analysis. So I know like for when you analyzing the tweets, it's all like a lot of textual information. So I'm just curious, did you use any techniques for text mining?
Other than everything that I discussed for EDA and like a technique that I applied, I don't think I got to use any other text mining technique. But just to add to that, actually, maybe I'm not answering your question by saying this, but the sentence analysis I have done is mainly on bigrams, trigrams, or n-gram analysis, which is part of the data representation and feature extraction. So this analysis can be actually used for LDA topic modeling and also for machine learning optimization. For LDA topic modeling, for example, if you have like common terms appearing on across the clusters or across the topic, then your cluster or your topic is no longer unique. So for that, I guess it's not really text mining, but you can introduce trigram, n-gram into the word pool that you are creating topics from. And that will create unique terms, unique word of a group of words for topic to be formulated. So that is one area you can apply that. And another is, I think I mentioned earlier, that sometimes machine learning parameters for optimizing its performance, you can sometimes specify n-gram. So then you can you can add that feature as a part of the machine learning optimization process. So there's two. But I don't think I applied any other text mining technique other than I discussed in this presentation.
So thank you very much for the presentation. I had a question online from the beginning, and that was like, when I go through the tweets and I want to analyze them, one of the main problems that I have is that they're full of fake accounts and also advertisements. So I wanted to know if there was anything that Kaggle had already done in order to eliminate those, or if you find something inside the data set.
Unfortunately, I don't think Kaggle was that organized to do that. And so I think they randomly pull the data and then they just made a structured data format for us to be able to compete with this platform. So, but I've seen a lot of things that should have been eliminated, or I realized that I sort of mentioned earlier that training data set had a target class 0 and 1 to indicate whether this tweet is disaster related or non-disaster related. And then when I was studying, like going one by one, I realized some of them should have been classified as 1, but it was classified as 0. So there's a lot of errors. So I realized, oh, it's a manual label. They didn't really pay attention too much when they were doing this. And yeah, there's a lot of things happen. So I don't think it was organized, but it was not that organized that we only think.
All right, this will be the last question, and then we're gonna start to head out.
Thank you very much for the presentation. I really enjoyed your presentation and also the idea that you made. Actually, I have a guess for the transformers and because my bird is trained on Wikipedia and also Google Photos. I've never used the model before, but I hear there's a model called Twitter that is specifically trained on tweets. I think maybe using that model, maybe can the embeddings for the tweets better.
I think my answer would be yes, definitely. I know they only tried 3 models, 3 transform models out of hundreds of other transform models that exist. I think you mentioned one site where you can pull one of the transformers to try. Hugging Face page is really another good place where you can get hundreds of transformer models and you can actually try. So I'm pretty sure that other than the models that I tried, I'm pretty sure there is another transformer model out there that could perform way better than what I have done. So yeah, definitely. I only tried this transformer model, but I learned so much from just trying doing transformer models myself.
All right, once again, please, round of applause. For those of you interested on continuing the conversation, we'll be meeting at the St. Regis almost immediately after this. Other than that, thank you once again to Northeastern University. And thanks to everyone for coming out.
Do you want to go home? Yes. Fine. You want to go drink? We're trying to worry me. Ja, det kan jag because it's so temperature sensitive. Hey, it's good. Hey, it's good. Yes. Hey, bud. How are you doing? Good. Yourself? Yeah, okay. Yeah. I know. This is a sheet. Oh, isn't it? Yeah. Good job, man. Very good job. Yeah.
all my thoughts, but yeah, thank you. It's came together a little bit late, but we got it.
And you know, you gotta base this stuff.
Yeah,
right? Like,
yeah,
that's
for
it,
sure.
In the beginning, when you first started, I guess it was sort of coming from other regions, but in the beginning, I remember it was quite a small room.
Yeah, it was a conference room in what, Cardinal Pass?
Yeah,
I remember when
It's good to see you.
when you was almost a guy named so you're getting better things. Remember we were at Quentin's office?
Yes.
And like everybody fit in one.
That was CBRE. I remember that. It was,
Come on, you don't know how to.
Yeah. Who are you?
Bring a decent face, please.
Yeah.
So that we know your name.
People with the drinks on.
Please.
I made a reservation for 12 people, and I'm like, geez, I hope enough this show. So I will be going. I just got to check with
Okay.
crew, but yes,
So
please.
my usual suggestion. Let's be irresponsible.
Yeah, please. Yeah. It should be under Matt, or yeah, I'm gonna guess it's under Matt. My name.
Okay.
Okay.
I'll go. Yeah, I'll go.
Okay.
You go?
Yeah.
And you also have not much fire, one shot.
So are you going?
That's
To
why-
the
I think so.
yeah.
Yeah.
Have you logged out of the I bet you that's still running.
I'm gonna do that.
Okay, cool.